So here, so if you take C1 here, yeah, I'll draw a small example here. Oh. Okay, again, post. The reclaim host. Okay, the reclaim host. Okay, so we'll again consider this matrix partitioned according to the structure. So this is 1, 2, 3, 4 is a block B. This is the block B. So H here is the graph G. H here is G minus B minus 1. That means H minus 2, 3, 4. Okay. So the distance matrix, I think we don't need to consider the whole matrix, just those relevant parts, AI plus BJ especially. So here, the distance from the cut vertex C1, which you have called vertex 1, okay, 2, 2, 3, 4. So to 2 and 4, the distance is 1, and to 3, the distance is 2. So this part is what we are calling the AIs. A1, A2, A3, 1 to 1. And similarly, the distance from that vertex to the vertices, the other vertices of H. So 5 it is 1, 6 it is 1, 7 it is 1, 8 it is 2, 10 also it is 2, 9 it is 3. Is that right? So now we want to know what is the distance, for example, from, let's say, vertex 3 to vertex 8. So here if you see, you can 1, 2, 3, 4. Okay. Or else 1, 2, 3, 4, same thing. So this is 4, wait, 3 to 8. So this is 4, which you can see is 2 plus 2. But why is it 2 plus 2? Because 2 is the distance from 1 to 3. That distance is 2. And then the distance from 1 to I should say the distance from 3 to 1. So the distance from 3 to 1, that is 2. Okay. Distance from 3 to 1, like this, that is 2. And then the distance from 1 to 8, this one, that is 2. Okay, so can you see that we'll consider starting vertex here on the row index and the ending vertex in the column index. So from 3 I have to go to 1 and then from 1 to 8. But I'm forced to do this because they are in different blocks and this is a cut vertex which is separating them. Okay. So the characterization of cut vertex is that there exist, one characterization is that there exist two vertices in the graph, so U and V, U and W, let's say, such that every UW path passes through V. Then V is a cut vertex. If and only V is a cut vertex. Okay. So in this case, another one is you have two sets. So V is a cut vertex if and only if there exist subsets or there exists a partition. Okay. Of the vertex at V of G, such that for all vertices U and U and W and W, every UV path, UW path contains V or passes through V. So that means the graph will look like this. V is a cut vertex, graph will look like this, so that you have some part here and some part here. That whatever vertex here you take, whatever vertex here you take, you have to pass through V to. So that's a characterization you can do. So that's what is happening here. We are taking one block. We take pendant block for this proof, right? Yeah. So here in this case we are taking pendant block. Otherwise you can take something in between also. So here we're taking a pendant block and a cut vertex as a pendant block because it will have unique cut vertex. That one we are taking, and that separates the graph into two parts like this. So is that yeah? This AI plus BJ, why it is it clear? If you take this as AI and this is BJ, okay. So then that row transformation process we're doing on the matrix, where we take every row is transformed as Ri changes to Ri minus R1 first row. Okay. And similarly, every column is transformed to Ci minus C1 first column. Okay, so from every row we are subtracting all these AI and BJ also. AI by the both.
One entry subtract row I.
Oh yeah, correct. Because only the first column. I was thinking all the columns. Yes. Yeah. So this will remain. That is. So these will actually remain as AI and BJ. that's true. Then the claim is that this matrix after transformation, this part becomes 0 because of that reason. All the AI and Bj get subtracted, and those are exactly AI plus Bj. And same thing happens with this part symmetrically. And yeah. Now the determinant of this transformed matrix DG, which is also equal to the determinant of the original matrix because this is row transformations. This is equal to determinant of this block. Yeah, this block multiplied by determinant of this block plus determinant of, yeah, now this part, right, including this much that submatrix times determinant of this remaining complement submatrix. That has to be.
So that determinant of DG tilde is equal to, even there that starts by root
that is actually oh, all right, this is just a 88. Here it is. Right.
Here, I can just do one of them is just a block, the other is just I will do induction on block. We do it for arbitrary also. Yeah, we do it for arbitrary also. In this case, I will just get it as in terms of the block B and the remaining block H. H I can do by induction, so it will be easy to write what I want.
That the previous observations are true for in general because at AI plus Bj everything holds in general. Whatever. Okay, so why is this determinant equal to this? So for that we have to consider the permutation representation, sum of. Yeah.
So why is this so? This what this is not.
Right, A only.
Like product I equal to 1 to A.
Okay. I'm thinking what I use DI sigma. This expansion will.
Determinant will be the Laplace expansion. So the claim is only those permutations. So it looks like there are lots of permutations, but some of them will give you 0. When will it go to 0? There are a lot of entities with 0. Let's see when will it.
Yeah.
When will permutation give us 0?
So this product is similar to that A cube, A power n proof and all we seen where you have zeros and ones. Here also it is not zeros and ones, but zeros are there. So this term will be non-zero only if all the Ti sigma is in this involved in this are non-zero. So if one of them is also 0, then it becomes 0. So when will any Di sigma D or D tilde I sigma I become 0? when will any d tilde I sigma I, I'll just say di sigma I, become 0? I mean, when will it fall here? So first of all, yeah, it doesn't matter if it's 0 because of anything here. It doesn't matter. We'll just account for the zeros coming from here. Yeah. So suppose sigma maps I to one of these.
One.
One. Sigma maps one, the first vertex. To any of the vertices in the first block. In that block. In the block B. Yes. Then what should happen? Notice that this is the distance, right? It's not some arbitrary matrix entry. This is the distance here. I mean, not the distance, but this particular matrix.
Image of 1 is some element of B. So whose image is 1? The cycle. So 1 goes to some element in B. Which element has image 1? So it's permutation. Which element has image 1? That you have. So that could be an element from 1 goes to some element B. Vertex B of B. B of B. Now,
AK is the number. So, yeah, some.
fine. And then who comes to 1? In the cycle that contains 1. So if you think of that sigma in cyclic form, 1 will go to some image of 1 in sigma, then that will go to sigma squared of 1, sigma cube of 1. Eventually, some element will come back to 1. So if that element that whose sigma is 1, if all the elements are in B, the cycle, then it's okay. If, for example, 1 sigma of, so the J is sigma inverse of 1, that's what I thought. Sigma inverse of 1 is the one who's feeding it. So if that sigma inverse of 1, that belongs to H, B belonging to H, then W belongs to H. Then what can you say? In the belonging to H. Then if somewhere your 1 went into B, then B, somewhere you went into H. See this B cross H, if there is an element from, what are the 0 blocks? Either you are going from B to H or from H to B. So if you go from B to H, definitely you will touch the one element of the 0 block and you will touch permutation will not happen. Otherwise you go from similarly from H to B. G to H and H to B both are will be 0. Both there any element in that cycle which goes from B to H or from H to B, then it is going to give you 0. So what is the only way to not get non-zero? Everything is if you look at all the cycles, disjoint cycles of sigma, it will be only in B, or every cycle, all elements of the cycle are in B, or all elements of the cycle are in H. Is it clear? This two people agree. Maybe you can repeat it. Who all agree? Who all don't agree with it? So what is the problem? Sometimes you will touch an entry from the 0 block, either the upper right or the lower left. When you touch such a 0 from the 0 block, if you go from, so you look at the cycle decomposition of the element sigma. So 1 goes to B, goes to dot, and then goes back W goes to 1. So sigma of 1, which is B, belongs to B, for example, and sigma inverse of 1, which is W, belongs to H. Then I'm getting such a sigma will not contribute. Why? Right. Why will one of the term be 0? You went from so sigma of 1 is there in both B and H with the vector. So 1, the image of 1 is in B, then image of that vertex is it in B, maybe it is in B, okay. But at some point sigma inverse of 1 is in H. So at some point you should have gone from some vertex of B to some vertex of H. Is clear? Then what will happen? If you go from some element of, so in that D tilde I sigma I, so somewhere they would have gone from some vertex in B to some vertex in H. So then what will you get? There you will get a zero. Correct. That's what I'm saying. So if you take one cycle containing the element of, so one will go to some element of B, element of B, but who's coming into H? Who's coming into one? That is an element of H. So somewhere it is B, somewhere there is a B to H transition. That transition is zero. Why will it be zero? Because that means the identity I sigma D tilde of I sigma I, that will be from element of B to element of H, which is the so element of, and it's not one. So one is already taken. Is it okay or is it not okay? More people clear that it's okay. Who are anybody else who's convinced? Anybody who's convinced? Okay, you are convinced. Why did you repeat once for the sake of classmates? So listen to what is your name? What's your name? Kranti. Listen to Kranti. So can you read?
Yeah, the only reason is the interest there are zero. We get the product will be the AIJ card product. If one entry belongs to that particular zeros, that combination doesn't contribute. So we are looking to only the combinations which doesn't give us those entries, the zeros, double zeros. So in order to do that, we only have to consider the combinations when all this IGs belongs to either B or to either H. Then only it's possible. Then only the product won't contain the zeros. So that's it.
Sure. Wait, your colors. Your colors. Anybody who's not convinced yet, I know what was it. Anybody else not convinced? Just raise hand. 1, 2, 3. I don't know. So maybe do one more. So maybe who's now convinced? One more. That's all. Can you repeat once more? You pay attention. You know those
expression. So if it's sigma of sigma is a constant term, and then there is a full product. The product terms, what are all? I will start from I 1 to n. So first term is d tilde of 1 sigma 1 into d tilde of 2 sigma 2.
So sigma 1 sigma square. And looking at the cycle, 1 sigma 1 sigma square. Sigma square of sigma 2.
You're not considering it in D1
I'm
to
not doing
D.
it as 1 to n. I do it in cycle. Yes, sir.
But then the product terms are.
No, I know all of them will come because once it will also be there. You're writing the product.
Okay, we will consider it like.
Yeah, considering the doing cycle decomposition, considering that one.
But is that necessary?
No, then it will be easier because 2, where is it? I don't care. 1 sigma 1. Sigma 1 sigma square 1. Sigma square 1 sigma 2 1. So you can eventually come back to 1. So you consider only the cycle containing it. It's better to think of that product as product over all the cycles of sigma. That may be easier. Because there at some point you need B, and then at some point you have because sigma 1 is in B and sigma inverse of 1 is in H. Then at some point there has to be a transition.
Or the other terms.
Other
I is in B and sigma of I is in
correct. Both. So in both cases you will have a problem. So that's what I wanted.
So I'll just say in the way that I understand.
Okay, sure.
So we just consider the product in the way they are written. I went from 1 to n. So like I sigma 1 sigma 1. Then second term will be d tilde of 2 sigma 2. Next term will be d tilde of 3 sigma 3. So in order to get all non-zero, we need each term to be non-zero in the product. So when will one term become 0? When you have d tilde of for some I sigma. This term in the matrix d tilde capital d tilde of j will be 0. So you can see if I belongs to one block, in the sigma of I belongs to another block, then you will get the integer. That's the only way. So then that's the definition. If for sigma I is in B and sigma of I is in another block H, then you get D tilde of I sigma I is 0. Then the whole thing will become 0. So to consider non-zero the whole expression, for every I, this should be the case. I and sigma should be in the one block, whatever block you are considering. If you are considering I is in B block, sigma of I should also be in B block for every I.
Okay. Okay. One more big connection. Yeah.
No, so that's an easy argument. So why is it not considered?
Fine. For me,
You just partition it into.
no, but then so for me, you look at sigma essentially partition cycle of sigma.
Yes.
Or
No, I got that. That is a. Yes. Yeah.
so it's H, take it as on the H B. That's why I write, if you write this product.
No, is there any advantage in considering? So in the intrinsic matrix the Harari formula, we have to consider cycles because we are looking at the cycle in the graph. The cycle will be observed in the graph. Here we are not doing that.
If you go B to H or H to B, you B or take it to sigma. Such that if you look at it in cycle form, the cycle of sigma is only H, not only sigma. Only such cycle.
Oh.
All other sigma. All other sigma.
Fine. Now my second problem is that is for each term separately. Each such term in the summation is for each term separately. No, that's different from what you said. That's what. All cycles are in for the same sigma, all cycles are in H, or all cycles are in B. No, what if one cycle is entirely in B and one cycle is entirely in H? That cannot happen. That, I think that doesn't follow from the argument. In the same sigma, so one cycle is entirely in B, another cycle is entirely in H. Is that okay? That is okay. The same sigma. But
It's equal to writing in one, but always in the H part, B part. So H part is the sigma prime.
okay.
B part is sigma prime. They are crossed with all sigma.
No, I was wondering how it's a sum of products. So if in one product you are able to split, how can you split the sum of products? Because if it appears here, there is another one which is that no, that part is okay. I was wondering. Okay, we can break it because all combination, all pairs, all combinations. That point I missed. Yeah. Yes. Sorry, something is happening here. No, it's automatically stopping for some reason. No, it's fine.
The other one also I give. So can you see that the example this 0.1? Can you try to work out? So it is you have to show it is a PD matrix. So how do you show? Positive element matrix you have to show. So I would suggest that you take calculate A plus A transpose. A plus A transpose. The half of A plus A transpose. So get the symmetry percent. So this we call it as a B. Okay, so what will be my B? Can you give me my B? Tell me the words. O half. One. Two. This is two. Yes, sir. Then eight. The 2 by 2 is 8. The 2 by 2 is 8. 2 by 2 is 8. Then half. Then 2. Then 7. So it is a strictly positive matrix. So can you see the leading principal minus? So what is my leading principal minus? Diagonal elements and then so say 1, then 1, 2, then 1, 2, 3. So all are positive. Determine. So what that so what is this is determined is positive. A1 B11 B12 and B21 and B22 and determinant of that is positive, and then the whole determinant of B. So if you take, say, for example, if you evaluate all principal minus, then what will be that? Alpha equal to 1, 2, then 3, then 1, 2, then 1, 3, 2, 3, 1, 2, 3. So Karp characterizations all principal minus are positive. So you can evaluate all these principal minus, you will find that it is positive. Is it right? All 2 by 2 principal minus are positive. So do you follow how we are calculating? So what will be that 1, 2? B alpha is 1, 2? 31. No, it will be 32 minus 1 by 4. that means is positive. Then 1 3 28 minus 4 24, that is positive. And then 2 3 56 minus 1 by 4, that is also positive. And the determinant is also positive. Okay. So A is positive definite, then all principal minus are positive, and then all leading principal minus are also positive is included, and then eigenvalue that in MATLAB you can calculate eigenvalues of B, it will also be positive. And so you can figure it out when it is positive definite. But the next one, every PD is PSD, but the converse is not. So if you write down the expression, you will see that all the determinants, all the, you take A plus A transpose and do the same way, you will see some of the principal minus are positive, 0. Right? And it is clear that 3 for alpha is equal to 3, it is 0. You take half A plus A transpose, diagonal elements are 0. For a PD matrix, diagonal elements has to be positive. So it is not a PD matrix in the case. Okay, PSPD matrix, I have already explained that if you write down the quadratic forms, 0 2 minus 1 0, it is a zero to minus 1 0 quadratic form, it will be x transpose x will be x1 x2. So if x1 is greater than 0 and x2 is less than 0, it has to be positive for all x. But that is not so. So it cannot be PSD or PD. So now you have to check whether it is PSPD or not. And it is not a symmetric matrix either. So to check whether it is a PSPD matrix, that you are calculating x transpose A, and you can see that x1 x2 less than 0. And since x1 x2 are opposite side, you can always figure it out that A transpose x is inside. Is there doubt? Any doubt?
This theorem 0.2.
Yes.
Symmetry not required.
Theorem 0.2, that all principal minus will be non-negative. That we have already checked. You can always check that. For example,
Is that true for even non-symmetric matrix?
yes,
Is it true for non-symmetric?
non-symmetric matrix. No, this is that all principal minus are non-negative. If A is positive symmetric, then all principal minus will be non-negative.
Even eigenvalue is non-negative
Eigenvalues also will be negative.
for non-symmetric. Because
But here I am not assuming symmetry.
for positive, definitely assume symmetric.
So here that if you assuming non-symmetry, so then you make it a symmetry and then find out only check for the leading principal minus. That's good enough. Otherwise, if it is a otherwise, then you can check all the principal.
So the above
Yes,
the positive for positive definite also it holds.
positive means it is strictly positive. No diagonal elements will be get that achieved.
Even without symmetry.
No, strictly speaking, if you want to check whether it is positive symmetric or not, you have to convert it into a symmetric one and see check only the leading principal. Because later on you will see for P naught matrix, so there also all principal minus are positive, but it is called a P matrix, it's not a PSP. Right? So obviously that in this example, it is not a this example, it is not a PSD matrix, it is a PSPD matrix. Now let us take example number 5. Every PSD matrix is P naught. But the converse is not. So you can see here that for this, no, that for the matrix A, is diagonal elements are greater than equal to 0, and determinant is also greater than equal to 0. So all proper pieces minus are greater than equal to 0, so it is P naught. But is it a PSD matrix? You can easily give a counter example. So if you have the this one that expression for the quadratic expression, this will be what? Right? And if it has to be PSD, this has to be greater than equal to 0 for all x. Okay. Now, one you take. 1 and 1 if you take is less than 0. Right? So it is not a PSD. So P naught matrix generalizes PSD. Similarly, every PD matrix is P. Every PD matrix is P. So, but A, so here A is a P matrix. How can you say? Diagonal elements are greater than 0 and determinant also is greater than 0. So it is a P matrix. But it is not a PD matrix. Why? We will have same approach that so this will be x1 square minus x1 square plus x2 square plus 2x1 x2. So this is x1 minus and so obviously if you take 1 then it will be 0. It is not a PD. But thing is that it is if you take that the expression, so it will be greater than equal to 0. Right? It will be greater than equal to, but if you take the this one that half a plus a has to, what will happen? So this will be 1 and this will be minus 1. This will be minus 1 minus 1. So you can see that it is definitely not P. It is definitely not P and also not PD. Because if you take half a plus a transpose, its leading peaceful minus should be positive, but it is not happening. Understood? Is there any doubt? Any doubt? Then next is this one. If you calculate all the principal minus, what is the principal minus? 1, 2. So if you take 1, 2, 3, 1, 2, 3. This is -2, -2, -3. So this is negative. Then alpha 1, 2. So this will be what? -2, -5, -1. So this will be 4 minus. So determinant will be -1. So similarly, 1, 3. We will have a negative determinant. So all will be and A13 will be so all are negative. So this determinant is negative, so it is the A matrix. So and similarly, if it is non-positive, then it is called a N. Yeah. For alpha equal to 1, 3, what will be the value? -2, that 4, 4 minus 5. So determinant 1, 3, A alpha so similarly 2, 2 also same. So you can see that and the determinant of A is -8. So all are negative. Understood? N not matrix understood? So now G matrix. Off diagonal entries are non-positive. So therefore it is Z matrix. Easiest. Now Z matrix. If you see this matrix, is it a P matrix? This matrix A. Can you find out whether it is a P matrix? Diagonal elements are positive. You can just work out quickly. Is it a P? So my concern is that this matrix, whether is it a P matrix or not.
Yes.
Yes. So that means it is G intersection. Now, if you find out the inverse of this matrix, it will be non-negative. Can you verify this? You can probably that use some internet, no? That inverse of the matrix, you can find out the inverse of the formula internet, whether it is non-negative. Yes, it is non-negative. Okay. A is this one. Now my question is the following. If you have Z intersection P, you are getting inverse non-negative. Right? You are getting a non-negative matrix, but any non-negative matrix will be that the reverse will be Z intersection P. See, if you take a Z intersection P matrix, it is non-negative, and if I take inverse of that non-negative matrix, what you have got? So what is the non-negative matrix you have got?
By 10 times. B11.
1 by 10.
Outside. B11. 131. 113. Yeah.
So you have got a non-negative matrix, and if I take inverse of that, I will get back the same G intersection P. But any non-negative matrix will not make Z intersection. So then, can you find out the class of non-negative matrices which will give this?
I think that is a little bit, no German.
So what are the properties should have? So this non-negative matrix has certain properties, but and I can get the this one G intersection P, but I do not know that any non-negative matrix inverse will not be given. Any non-negative matrix will not forget out. So if I give you a non-negative matrix, it will not be a G matrix. So when it will be a G matrix? When a non-negative matrix will be a G matrix?
That is why what is inverse to be.
You see that I am not keeping that character, no, that G intersection P is there, no? But inverse will not have, but you have got a P matrix also. Non-negative P, whether non-negative P will have a G intersection P. You have understood my question? I have taken a G intersection P, I have shown it is inverse is positive. Now I am taking a positive matrix. And then I am putting the condition P also. Because there is no point in putting G there, because that non-negative matrix cannot be a G matrix. So a non-negative matrix, a non-negative P matrix, whether it can be a inverse can be a G matrix. You can easily work out a counter example. Can you quickly work out a counter example? Get a non-negative P matrix. Give me a non-negative P matrix. And then I will compute the inverse. Right. I can put something like this, say 3, 5, 7 in the diagonal. Then this type here, each of is 1. Will it be P matrix? 3, 5, 7, this type here to be 1. Will it be P matrix? You tell me the determinant. I can see that 3, 1, 1, 1, 5, 7, then 3, 1, 1, then 1, 5, 1, 5, 1, 1, 5, 1, then 1, 1, 7. Positive. So it is a P matrix, but it's in what is its inverse? 3, 1, 1, 1, 5, 1, 5, 1. 3, 1, 1, 1, 5, 1, and then 1 on 7. What is the inverse? I do not know whether this will be counter example or not. So what is the inverse? This particular.
Any particular properties, some complicated.
No, 3, 1, 1, 1, 5, 1. I just want to compute the inverse.
So it is like 0.36 minus 0.06. Inverse is going to be
So we can
0.36.
0.36.
Which is equal to
1 by 4 outside.
okay.
70. 1 by 46 in the outside and 40, 70 minus 3 minus 3
So you are not getting a G matrix.
No, it is a
Oh, it is getting a, you are getting a G matrix. Because this is the, I have made the diagonal elements so big, no? Probably that's why it has happened. But you can get a counter example. Do you have a counter example? Whose inverse will not be G. Yes?
Matrix of size 2.
Can you?
Matrix of size 2 where the boundary from.
Size 2 you can say, but I will be happy that if you can give a size 3. I'm not very hopeful about size 2, no, but it is not carried forward many times. What is? Huh? Yes. What is that?
0 2 3. 2 0 diagonal is like 0.
No, diagonal, no. Diagonal 0 is not allowed.
But it gives this non-negative matrix. You say non-negative.
So G intersection P will be non-negative. Okay. You can give me a non-negative matrix. And then inverse will be what?
Inverse is not a G matrix.
So your matrix is 0,
2 3
okay,
and 2 0 4
2, 0, 4,
and 3 1 0.
3, 1, 0. It is a non-negative matrix. And but it is not a P matrix.
It is not a P matrix.
But can you put something in the diagonal? Because you cannot make it a P. Because if you put a bigger one, the diagonal.
So the A is equal to 22 3 half.
A is equal to
22 half row. 22 3 1. 34 second row. 34 23 1. And start with 34 3 1.
you are saying this. Is it a P matrix?
It is not a P matrix.
No, I won't say P matrix. Non-negative P matrix. So you are getting a counter example. So there is one thing that all strictly positive matrix, if you take an inverse, it will not be a G matrix. That is true. Now we would like to see if you impose the non-negative instead of strictly positive P matrix, whether the inverse will be G. I think it is not difficult. It's getting it.
In example 0.9, that matrix A.
What is that?
That example 0.9.
Okay.
If we take that matrix, P matrix, but the inverse is not a. The inverse is 1 by 10 Q 1 1.
So you take this matrix as a P matrix, but I said it is a positive number. You have to take positive weight, strictly positive weight, which is also a P matrix. Okay, so if you replace it -1 by 1, -1 by 1, will it be a P matrix? So if you take code 1 1, 1 code 1, and 1 1 code, will it be a P matrix? Perhaps. You have to say only the what is the determinant. Huh? What is inverse? Let the yes.
One, four, one, that matrix has become a four.
Determinant for, but it's inverse G matrix
Yes, symmetric.
because it is diagonal determinant. No?
Yes.
So that is the
That
and what is that?
My matrix is 18, 1, 3.
18.
Half one is 18, 1, 3, 17, 4, 2, 23, 2, 5.
Is it a B matrix?
This matrix.
Yeah.
This matrix.
But it's inverse.
Inverse is not given.
Just recheck from this side.
I get element in at the position of 2, 3, 0.2. Of diagonal element is not. Do we need to start with a non-entropy matrix or just a non-entropy?
No, I have a that I'm taking a strictly positive. Non-negative matrix you can take that other some entries could be 0, but what I want is that it should be P matrix. There, this is not the only example. If it is correct, there could be plenty of examples.
We are looking for strictly positive matrix. Minus is not given. That's all.
Inverse is not in.
Start with the strictly positive matrix.
So, but you have to see whether it is P or is it P?
Yes.
This matrix is it P?
Yes, yes.
Yes, sir. Is inverse?
It's inverse, 8, 2, 3 element is positive and all other of diagonal.
All are negative. No.
There are 2 of diagonal elements which are positive. And all other are.
Okay, so this starts as a motivation to investigate the class of positive matrices whose inverse is negative. So your paper starts from here. So that so what is the subclass for which inverse will be positive? For which inverse will be G matrix? Okay. This Burman and all, no, everybody worked on this one, and that there are a number of people who is working on this, and you see that inverse G matrices, there are a number of papers. You can search it in the Google. That inverse G matrices, there are a number of papers. Okay. Right? Okay. Now, now let us take example 16. Let us take example 16. Can you check whether it is inert matrix or not? By the way, you know that to find out what is co-positive matrix, right? Co-positive star is very clear. For example, this matrix is a co-positive matrix, but not a PSD matrix. Can you prove it? You can have a, but here you can see here that if you take the A plus A transpose and see that all P minus are leading P minus are not non-negative. So it is not a PSD matrix. Right? But since this is a strictly positive matrix, it is a C naught. Right? And this is another example that all strictly positive matrix need not be a P matrix, and it inverse also need not be a G matrix. So that this area is quite open, and that people are investigating on it, and this makes sense that to investigate the class of inverse matrices. There are various reasons algorithmically it has importance. Now check for the problem 16 whether it is the inert matrix or not. If somebody can do it and write it in the board, that will be nice. Example number 16, whether it is the inert matrix. Inert means it is semi-contour. So that I want only the check that it is the inert matrix. So you have to check on the first principle. X1, X2, X3, etc. You have to adjust all that. And it's very easy to see if X1, X2 is, you can partition this matrix. You can partition this matrix, and one can easily prove that it is the inert matrix. You can present the today's class is- So it is done. Now we will do the PPT. So now you have to do a PPT. So PPT is that you can check. So this is the this also you can check. So what happens? Example of So here that I want to find out the principal pivot transform. So it has to be, you have to get it with respect to alpha 1, 2, 3, then 1, 1, 1, 2, 1, 3, 2, 3, and then 1, 2, 3. So when you take alpha is equal to 1, when you take alpha is equal to 1, then what will happen? That you have to write down this form. This particular form. And so it will be, this will be alpha alpha 1, and this will be alpha over alpha, and this will be alpha over alpha. Then here this will be A alpha alpha inverse, that A alpha alpha inverse. Just a minute. You can see here, when you partition it, so this is your formula. This is the PPT. So you have to compute A alpha alpha inverse. I have not just now I have shown. This A alpha alpha, A alpha alpha 1, A alpha over alpha, A alpha over alpha. And then it PPT. PPT is this. what do you want me to write? So here, same name is there, no, that, here you can write the demand. Instead of A, you can write it there, this is the, I can call it as A, then it will be clear. So A alpha alpha, A alpha alpha what? A alpha what alpha, and A alpha what beta. And then you have to get the PPT. So this will be A alpha alpha inverse. Yeah. And then M alpha alpha 1 is minus A alpha alpha inverse A alpha alpha. Then this will be A alpha 1 alpha A alpha alpha inverse. So this you have to compute, right? So once we compute this, you will get the PPT. So M will be PPT of A. M is PPT of A with respect to alpha. Right? And so like that you will get PPT. This is for alpha is equal to 1. Then alpha is equal to 1, 2. Then alpha is equal to 1, 2, 3. Then 1, 3. Then 2, 2, 3. 3. See, and that when 1, 2, 3 means the matrix itself, no, the inverse, no. So if you compute all this, then you get the PPT. So similarly, that for this also, that it will be that you have to get so many inverses and all. So you can use some MATLAB code to do that, to check whether all PPT are. You can compute it and then check whether the matrix belongs to the specific class or not. If all its PPTs are inert, then we will say it is inerted. If all its PPTs are inert, we will say it is synerted, fully positive or fully semiconductor, and then work on this. So that's why that I said that if you want to work in this class, that you need to have some computation power. Otherwise, you can't afford to work in this. You can see here that so many people you have to calculate, and then only you can compute something. And once that n grows, no, size of the matrix grows, then number of PPTs also grows. So we have to check all this. But people have done heavy computations and then got the result. So I'm sure that if you are computationally you can do something and people will be able to get something else. Okay, so this is already there is 4 to 5 minutes. It's already right. I'll leave it here. And tomorrow I have one more. Okay. So I hope in this workshop that we will be spending one week and we will have something to take care of. To do for further. And what is the distribution? How many of you are from the institutes you belong? Who are from IITs? IIT, Guwahati, Hyderabad. You are from? IIT Madras. So you are working with? Yes, and so they are also you will be using this technique. That they are also working on technical training. Yes.
I'm working in spectrography.
Spectrography, not on this. And who else? So you are from? IIT Madras. And who else? You are from? Same IIT Madras, so it's very big group. And then what about the other IIT? IIT? Kharagpur. So you are working with? Purtima Pani. Yes? IIT Guwahati. You are working with? Oh? Okay. What about the other institutes? United? Andhra Pradesh. You are working with whom? Okay. Who else?
I'm from IIT Gandhinagar.
IIT Gandhinagar. So you are working with whom?
Dr. Rajesh Mathur.
Not so he also works in similar stuff.
Yes.
So who is there? What about others? IIT Guwahati. Working with? What about you? IIT Guwahati. Working with? Sukanta. And what about the remaining? You are?
NIT Calicut.
NIT Calicut.
Right. Then we can.
Then
ICT movement.
okay, so they are working on these things, I mean, or graphs.
I have a co-guide from SNU. So I work with him.
You have a co-guide from?
Iwsmga University.
Yeah, so who is the co-guide?
Satyanarayana Reddy.
Satyanarayana Reddy.
Thank you, Anand.
Yes. Okay. And who is that? Pune University. Pune University. Okay. What is it? Then, so it's good that you are taking interest on this kind of thing. And all of you that want to pursue this, right? What about Tamil Nadu? So there, who is working? You are working with whom? Okay, Chandrasekhar. Okay. Yes.
NIT Calicut.
Okay. Okay, so that it's good that many of you are joining the family of special matrices. So almost you can see that we know almost many each other. Then.
need to